Welcome to the introductory video on acids and bases for organic chemistry. If we remember general chemistry, acids and bases, we have a couple different kinds. We have the Bronsted-Lowry definition, which is primarily what we will talk about in organic, and then we have Lewis acids and bases, and that will be a separate video. For Bronsted-Lowry acids and bases, we think about an acid as a proton donor, and we think about bases as proton acceptors. For Bronsted-Lowry, we're really thinking about protons being put on and taken off of molecules. And remember, a proton is a hydrogen that does not have an electron. A hydrogen atom from the periodic table has one electron, and a hydride has two electrons, and that has a negative charge. In this case, we are talking about a hydrogen that does not have an electron. Also recall from general chemistry that we can have an acid, which is our proton donor, reacting with a base, which is our proton acceptor. And on the other side of the equilibrium arrows here, we have the conjugate base, which is the base that is left after the proton is donated, and we have our conjugate acid. And our conjugate acid is the acid that is left after a proton has been accepted. And so we have our acid that goes to our conjugate base with the removal of a proton, and we have our base with the addition of a proton that goes to our conjugate acid. A conjugate acid results when a base accepts the proton. A conjugate base results when the acid gives up a proton. So why don't you try? In the following example, label the base, the acid, the conjugate base, and the conjugate acid. And if we look, we can see that this has a negative sign, so that gives us a hint. Then we look here and we see, okay, well, we're given some hints here because it looks like that might be the proton that's donated. But let's go ahead and look at our products and see if that's the case. So over here, we see this molecule right here. Here's that proton that was on our water and then now got transferred to our oxygen here in the alcohol. And so I think I have it figured out. So work with me here. I believe that this is the base and this is the acid. And now over here, because this was our base and it got protonated over here, this now is our conjugate acid. The other way to confirm this is to think if we were going in the reverse direction, this would act as our acid. And so that becomes our conjugate acid. And then of course, the only one left here is the conjugate base, and that is true. If we think about the reverse reaction, this is the thing that accepts a proton. And when we have a base, what it turns into is our conjugate acid. And if we have an acid, what it turns into is our conjugate base. So we can think about how it starts and how it ends in terms of determining the conjugate acid and conjugate base. Or we can say, if we look at the reaction in the reverse direction, this is going to act as our acid and this is going to act as our base. And you can solve these problems either way. And so curved arrows in reactions is a little bit different than in resonance structure. Resonance structures, we could only touch the lone pair electrons and the pi electron. But when we're making and breaking bonds in chemical reactions, we can actually access the electrons that are in sigma bonds. So when we used curved arrows to draw reaction mechanisms, we will be making and breaking bonds that are involved in the process, and we're going to show electron movement. If we were taking this situation where we have a base, which is negatively charged, the thing that's negative, the thing with the extra electrons, is going to be where our arrow starts. Just like in resonance, we start where the electrons start. We have the electrons here, and they are going to reach out and form a new sigma bond with this H right here. That H cannot have two bonds, so the two electrons that are in this bond right here hop up onto the atom that the H is being removed from. Here is our base, here is our acid, and then over here we have our conjugate acid and our conjugate base. We look at electron movement. We see these two electrons here form a new sigma bond with the H, and that's shown right here. And then these two electrons hop up onto the atom A and become negatively charged. So these curved arrows are the same ones that we used in resonance. The tail of the arrow has to start where the electrons are, and then the head of the arrow is where the electrons are going. But in this case, we can actually make and break bonds. And so we're actually talking about the physical movement of electrons. Remember in resonance, we said that it was just kind of a picture that we would take instantaneous. And those electrons were really an average. They were kind of shared, and it was like a hybrid instead of the actual contributors existing. And so, but these chemical reactions are actually the movement of the electrons during a chemical reaction. Okay, here's one more example. This reaction is already labeled. So here's our base, here's our acid. The base is where the electrons are, the extra electrons. That's where the tail of the arrow starts. So we move from this pair of electrons and we make a new sigma bond with this proton here. And then that proton can't have two bonds. And so the electrons in this bond hop up onto the oxygen here. This base gets protonated and becomes our conjugate acid over here. The hydroxide ion becomes water here in the conjugate acid. And our acid here, which is acetic acid, gets deprotonated or donates a proton and becomes the conjugate base. So that's how that reaction works. So the arrows that we would draw, you start where the electrons are and you draw the arrow where they're going. So these two electrons are going to become a new sigma bond in between the oxygen here and the H here, which is not shown here, but if I was going to draw it, it would look like that. So it's that new bond. And then the second arrow shows that these two electrons in that sigma bond hop up onto the oxygen. And so they're now here. And so I hope that makes sense. Using arrows in acid-base reactions is pretty simple. But the good news is we actually get to touch the sigma bonds now. One thing that we may think about is that the base attacks the acid using a pair of electrons. I said the electrons here reach out and form a new sigma bond with that hydrogen. You can think about it either way. The acid cannot lose its proton without the base taking it. So all acid-base reactions occur in a single step. And the mechanism here shows two arrows indicating that the pairs of electrons move simultaneously. One shows bond breaking and the other shows bonds being formed. And those are going to happen together at the same time. It's called concerted, and it's a single step. Even though we see two arrows, that's going to happen at the same time. If we look at another example of a chemical reaction with curved arrows, we'll start here. So if you're unsure how to start, what you might do is look at the product. So the product of this first step is shown here, which is a protonated alcohol. If you think about that, our alcohol here gains a proton and the hydronium ion here loses a proton. And so we can be thinking about this as our base and this as our acid. What happens is the lone pair on the oxygen right here reaches out and forms a new sigma bond with that proton there. And in exchange, these two electrons hop onto the oxygen. And so our product shown here is in fact the conjugate acid. And in this step here, our conjugate base would just be water. And so that's the first step of the reaction. It's a proton transfer where we have an alcohol and a hydronium ion, and that proton is transferred from the hydronium ion onto the alcohol to give us this protonated alcohol, which is our conjugate acid. And so now if we think about the second step of the reaction, we will be taking the answer to our first step and we're going to be losing water. So that minus H2O just means that water leaves. And so what has to happen for water to leave is this sigma bond needs to be broken. And so the two electrons that are in this bond hop onto the oxygen, creating water, which is a nice stable compound. So it makes perfect sense that that would leave. But what we end up with this carbon piece is a carbocation shown right here. Because this carbon right here loses these two electrons, it now becomes a carbocation right here. That is the second step of the reaction. We start with a protonated alcohol shown here. We lose water or water leaves and we end up with a carbocation. And so that is the second step. If we talk about the third step of this reaction, we start with the carbocation and we have our molecule of water. And in this case, what happens is the water, and you can tell from these arrows, pulls off this proton and creates a double bond. Now, if you were unsure how to do this, You might look at the product first and see that we're forming a double bond. So we're thinking about that carbocation being satisfied by having a pi bond added. And so the way we do that is the 2 electrons from our water molecule here reach out and form a single bond, a sigma bond with this hydrogen here. That hydrogen can't have 2 bonds. So the 2 electrons from that bond hop in to satisfy the carbocation, right? So these 2 electrons hop over and form a double bond here, giving us our final product. Now, don't stress if you're thinking, oh my gosh, this is absolutely crazy. I have no idea what just happened. I'm just showing you that using curved arrows in chemical reactions, it can make a lot of sense. 2 things. If you just look at the product that's formed in each case and then figure out how the electrons move to get it there. Or you can also look at the arrows and just follow the electron movement as you move through the multiple steps of the reaction, and you can get your products that way. So I hope that makes a little bit of sense. Don't worry, you won't have to do anything like this right away, but I did just want to show you that pushing electrons is fun and exciting and new. And the coolest part is now that we're doing chemical reactions, we have access to all of those sigma bonds. We can make those sigma bonds, we can break those sigma bonds. Before long, you will be drawing mechanisms like this one easily. For now, though, don't worry about anything except for just being able to follow where those electrons go, specifically in this chapter for proton transfer. Okay, there you have it, an intro on acids and bases. Next up, details about acid and base reactions.